Here we are on the last topic of this chapter, colligative properties of solutions. A colligative property is a physical property of a solution. It depends only on the number of solute particles in the solution, not on their chemical identities. Please pay attention to this part of the definition. The colligative property, of course, you need to know it is a physical property. Well, other than that, you need to know this property depends on the solute particles. Interestingly, it didn't say the concentration of the solute, but solute particles. What does that mean? Well, at the later part of this chapter, we're going to focus on that. We're going to explain that, what it means. All right, let's move on. There are actually 4 kinds of properties that falls under colligative properties. Vapor pressure lowering. A solution will have a lower vapor pressure than the pure solvent itself. Boiling point elevation. A solution will have a higher boiling point than the pure solvent itself. Freezing point depression. A solution will freeze at a lower temperature than the pure solvent itself. And osmotic pressure. A solution will generate a pressure that is called osmotic pressure. What is that? That will be the topic of our next episode. In this episode, we focus on the first 3. Vapor pressure lowering. Adding a non-volatile solute to a solvent lowers the vapor pressure of the resulting solution below that of the pure solvent. What does that mean? Well, how do we understand that? Think about this. We have a pure solvent. We have our solution. Assume you're put them in an enclosed container, both of these in an enclosed container. We're doing the evaporation experiment. Since the solute is non-volatile, so only the solvent particles will evaporate. Remember those evaporation experiment we did? Now, in the case of solvent, a solution, some of the surface area will be occupied by solute particles. As a result, at any given time period, there will be less solvent particles evaporated than the pure solvent itself. Or we can claim the rate of evaporation is faster in pure solvent than that in the solution. If the solution evaporates slower, eventually, when it reaches equilibrium with the condensation of the particles, it will need a slower rate of condensation to equilibrate with the evaporation in the case of solution, which means when the equilibrium, evaporation and the condensation, when the equilibrium of the 2 processes is reached, there's less solvent particles above the space in the solution. Therefore, the vapor pressure of a solution will be lower than that of the pure solvent. I hope that makes sense to you. Boiling point elevation. A solution will boil at a higher temperature than the pure solvent itself. Why? Well, it is not that hard to understand now. If you do understand the vapor pressure lowering property that we just discussed a minute ago. We learned some time ago that a lower vapor pressure always results a higher boiling point. Why? Because boiling point is the temperature needed to bring the vapor pressure to the external pressure. If the vapor pressure is lower, now you need higher temperature to bring it up to the external pressure. That's why the boiling point of a solution will be higher because its vapor pressure is lower than the pure solvent. Freezing point depression. A solution will freeze at a lower temperature than the pure solvent itself. Why is that? Well, let's think about this. Let's think about what happens when a liquid freezes. Temperature drops, particles move slower and slower and slower. Eventually, the particles will take fixed positions. They form a patterned structure. You see there are different shapes in crystals because each particle takes a unique position. They form a fixed patterned structure. Well, if there are solid particles in the solvent, in the liquid, it interrupts the formation of that pattern required to form the structure. Therefore, you need even lower temperature to stop the movement of those particles or to make the particles take a fixed position. That's why the freezing point is lower for solutions than the pure solvent. Well, as misgenders, we use this property a lot. Usually during the winter after a big snow, what do? We spread salt on the road, on the snow. When we spread salt, what happened? The snow will melt. Why? Here's the answer. When you spread salt on the ice, the solution formed has a lower freezing point now, so it will exist as a liquid instead of solid. So the freezing point is depressed. Therefore, the snow melts. All right, we have explained the 3 out of the 4 colligative properties. The last one, osmotic pressure, will be the topic of the next episode. Now let's look at how do we utilize these properties in real world or in question solving. Comparing the colligative properties, which means they will ask you to compare maybe vapor pressure, boiling point, freezing point. Either one is asked, is the same question, colligative property question. So comparing the colligative properties of different solutions. Remember, colligative properties depend on the number or the concentration of total particles. Total particles, not the concentration of the solid. What does that mean? It means the number of particles present in the solution depends not only on the concentration of the solute, but also on whether the solute breaks up into ions or not. No, I have no clue what you're talking about, Dr. Yang. Well, let's use an example to go through this. The example is a question. Which of the following solutions has the highest number of particles in the solution? A. 1 liter, 1 molarity glucose. In 1 liter, 1 molarity glucose, we have 1 mole of glucose, basically. B. 1 liter, 1 molarity sodium chloride. We actually have 1 mole of sodium chloride in this solution. C. 1 liter, 1 mole calcium chloride. We have 1 mole of calcium chloride in this solution. 1 molarity means 1 mole in a liter. Right now, all of them is 1 liter. All right, so which one has the most number of particles? If you look at your solute concentration of particles, all of them have 1 mole of solute. However, glucose is a molecular compound. Every glucose molecule, when it is dissolved in water, it stays as 1 molecule. So in this solution, we have 1 mole of particles. The number of particles is the same as the number of molecules because each molecule stays as itself in solution. In the case of sodium chloride, we might not have talked about that yet, but let's make this clear to you at this moment. Ionic compound, sodium chloride is an ionic compound. When an ionic compound is dissolved in water, it breaks into ions. They do not exist. Sodium chloride does not exist in solution as NaCl. It exists as individual sodium ion and chloride ion. Therefore, 1 mole of NaCl will result 2 moles particles. Does that make sense to you? Because each NaCl generates 2 particles, 1 sodium ion, 1 chloride ion. If you have 1 moles of NaCl, you have 2 moles of particles. If you understand the second one, the third one becomes easier. Each CaCl2, calcium chloride, will generate 1 calcium ion and 2 chloride ions. Therefore, in the third solution, solution C, you have 3 moles of particles. Does that make sense to you? So this question is asking you to compare the number of particles. Now we get an answer. C has the most number of particles. It is 3 times as many as number 1. B has the second most number of particles. It doubles the number of particles for A. Yep. Now here's another question. Which of the above solutions has the lowest vapor pressure or the highest boiling point or the lowest freezing point? All right, like I said, asking about vapor pressure, boiling point, freezing point is the same question. This question is asking you which one has the strongest colligative property. Whichever has the most number of particles will have the highest or strongest colligative property. Therefore, solution C will have the strongest colligative properties. Solution C will boil at the highest temperature, will freeze at the lowest temperature. It will have the lowest vapor pressure. Does that make sense to you? That's it for this time.